Assalamu alaikum. I will talk today about the Bohr model and the quantum numbers. First, Bohr model, نموذج بور. This model depends on the following assumption. Number one, electron in a hydrogen atom moves around the nucleus only in certain allowed circular orbits. إنه إلكترون ذرة الهيدروجين بيدور حول نواة الذرة في مدارات دائرية الشكل. طبعا راح نشوف بعد هيك إنه هذا الكلام مش صحيح. السبب إنه الدوران صح حول النواة لكن ليس في مدارات دائرية. Number two, Bohr's model gave hydrogen atom energy level consistent with the hydrogen emission spectrum. إنه هذا النموذج يعطيك أو بيبين لك إنه مستويات الطاقة في ذرة الهيدروجين تتوافق مع اللي هو طيف ذرة الهيدروجين الناشئ عنها اللي هو طيف منفصل زي ما عرفنا باللكتشر الماضية. Ground state, which is the lowest possible energy state when n is equal to 1. اللي هي حالة الثبات في الذرة طبعا لما بيكون عندك الإلكترون أو الفوتونز في المستوى الأول من الطاقة. طبيعي هذا الرسم اللي على اليمين اللي هو Energy Level Diagram بيمثل لي كيف توزيع مستويات الطاقة في ذرة الهيدروجين. هنا هذا المحور صعودا الانرجي بتزيد. فهي الخطوط اللي شايفينها ثلاث أحمر وأخضر وأزرق هي ناشئة عن الترانزيشن لإلكترون من المستوى الثالث إلى المستوى الثاني في الأحمر والمستوى الرابع للمستوى الثاني في الخط الأخضر والمستوى الخامس إلى المستوى الثاني في اللون الأزرق. طبيعي هذه كلها عبارة عن ترانزيشن وهي emission يعني انبعاث طاقة وكل خط فيه له لمدة تحدد له لمدة طبعا من اللي هي الانرجي بتساوي أو دلتا E بتساوي HC over لمدة. emission يعني انبعاث طاقة. العكس إذا كان الانتقال للإلكترون من مستوى إلى مستوى أعلى طاقة هنا بيكون عندي absorption نحتاج إلى طاقة زي ما راح نشوف later. In this slide here, this figure shows the circular orbits اللي هي المدارات الدائرية في هذا الرسم من N1 إلى N5. Also we have a transition from N5 to N2, transition from N4 to N2, transition from N3 to N2. And each transition is characteristic by a color code. Here we have a red, we have a green, we have a blue. As delta E decrease, we have longer wavelength. يعني كلما قلت الطاقة بين المستويين اللي بينتقل منها الإلكترون بصير عندك طول الموجة أطول. وهذا fits أو يتوافق مع اللي هو الإكسبيرمنتال spectrum of hydrogen. The most important equation to come from Bohr's model is the expression for the energy level available to the electron in the hydrogen atom is given by equation 7.1, where energy is equal to minus 2.178 into minus 18 joule multiplied by z square over n square, where z is equal 1 for hydrogen, atomic number of hydrogen is equal to 1, and n is equal 1, 2, which is the level, energy level, 1 or 2 or a 3 integer number. We have this equation here. Calculate the energy emitted from a transition of an electron from level 6 to level 1. Here in the diagram, I can draw this here. N is 6, N n final 1. So we have an electron in level 6. This will move down or transition to n equal 1. So this is n initial, level 6 initial, and level 1, which is the final. Then determine the wavelength emitted. We have to calculate delta E first, then we have to calculate lambda. From the above equation here, we can calculate energy of each level, as shown here. For N6, we have energy for the level 6 equal, substitute minus 2.178 10 to minus 18 joule multiplied by 1 square over 6 square, which is 36. This gives us minus 6.050 10 to minus 20 joule. Energy for level 1, same thing, is equal to minus 2.178 10 to minus 18 joule. Then delta E is equal the final level, which is energy of level 1, minus the energy of the initial level, which is level 6. Subtract each from each other gives minus 2.117 to minus 18 joule. The negative sign here means that the atom has lost energy. Negative sign, negative mean atom lost energy. Then, to calculate the wavelength of the emitted photon, we can calculate this by this equation. Delta E equal Hc over lambda. Rearrange this equation will give you the lambda equal Hc over delta E. Then substitute Planck's constant is a constant given, and c, which is the speed of light. Delta E, take the absolute value of delta E from the previous step. Then you calculate lambda in meter here. If you want it in nanometer, just multiply this by 10 to 9, and this will give 93.8 nanometer. Next, here we have another example or exercise, which is shows that how the energy is quantized in the hydrogen atom. This question, calculate the energy required to excite a hydrogen electron from level 1 to level 2. So here we have the opposite case. Here we have an initial equal 1, and final equal 2. So we have an electron here in 1 in the first level. This will goes to level 2. So this is absorption. We need energy. Okay, so we need to calculate the energy delta E. Then we need to calculate lambda of the absorbed light. By applying the same equation there, but we can combine them together in one step, we can get the following. Delta E, which is equal the energy of level N final minus energy of level N initial. And this here is equal to minus 2.178 into minus 18 in brackets 1 over N final square minus 1 over N initial square. So substitute now this equal minus 2.178 10 to minus 18 joule multiply by 1 over N square final اللي هو 2 1 على 2 تربيع يعني 1 على 4 minus 1 على 1 هذا الكلام بصير عندي ربع ناقص واحد يعني ناقص 75%. ناقص 75% في ناقص 2.178 10 to minus 18 بيطلع عندي بالبوزيتيف اللي هي 1.634 10 to minus 18 joule. Positive value here for E or delta E indicates that system has gained energy. We required energy. Gained energy. Now calculated lambda. Lambda can be calculated by HC over delta E. And this is equal to Planck's constant 6.626 10 to minus 34 joule second multiplied by speed of light 3.0 10 to 8 meter per second divided by delta E 1.634 10 to minus 18 joule. And this is equal to 1.216 10 to minus 7 from calculator meter. Same thing, if you wanted to nanometer, to change it to nanometer, just multiply this number by 10 to 9 and this will give you 121.6 nanometer. And this is the lambda or wavelength absorbed. Here we have a summary for Bohr models. The model correctly fits the quantized energy levels of the hydrogen atom and postulate only certain allowed circular orbits for the electrons. إنه التوافق الصحيح بين المستويات الطاقة لذرة الهيدروجين بأنها محددة، طاقات محددة، وإنه بدور حول النواة في مدارات، بس هو طبعا اعتقد إنها سيركولر يعني دائرية. هذا خطأ. من المآخذ على هذا النموذج عدم صحته، إنه هذا works only for hydrogen. هذا يعني ممكن تطبيقه على ذرة الهيدروجين فقط، أما باقي الذرات لا. وإنه الإلكترون move around the nucleus in circular orbits. إنه الإلكترونات بتدور في مدارات دائرية الشكل. طبعا بعد هيك راح نشوف إنه عدم صحة هذا الكلام، إنه صح بتدور حول النواة لكن ليست في مدارات دائرية أو مسارات دائرية، هي كل فلك له شكل. Now we have this exercise. Which transition results in the longest wavelength? Transition from n equal 5 to n equal to here 5, for example, here 2. This is A transition delta E1. Transition number B from n equal 4 to n equal 2. This is delta E2. Third or C, n equal 3 to n2. Here B, here C. As you see here, the energy gap decreases going from A to B to C. As the energy gap decreases, which means that we have longer wavelengths because they are inversely proportional to each other. Here we have the equation lambda equal HC over delta E. Inversely proportional. طبعا كلما قلت دلتا E أنا في المقام بدها تزيد وتصير أطول طول الموجة. In this slide here we have the quantum numbers, الأرقام الكمية. Solving Schrödinger equation for hydrogen atom, we find many wave functions or orbitals that satisfy it. Each of these orbitals is characterized by a series of numbers called quantum numbers. يعني حل معادلة شرودنجر بيعطينا أرقام كمية اللي هي شرودنجر equation عبارة عن H psi equal E psi. It's mathematical. H is a Hamiltonian operator. Psi is a wave function in three variables, r, theta, and phi, in the polar coordinate, where E is the eigenvalue. So solving this equation will give us three quantum numbers: N, principal quantum number; L, angular momentum quantum number, الرقم الكمي الزاوية; and M sub L, magnetic quantum numbers. So principal quantum number N, this related to the size and energy of the orbital, هو حجم وطاقة الفلك. N value from 1, 2, 3, etc. to infinity. So an integer number starting from 1. Number 2, angular momentum quantum number L, الرقم الكمي الزاوي L. L value اللي هي بتاخذ القيم التالية from 0 up to n minus 1 for each n. يعني إذا كانت n واحد معناته في عندي فقط قيمة واحدة اللي هي الصفر. إذا كانت n 2 في عندي 0 1 وهكذا. L is related to the shape of atomic orbitals, and sometimes we call it the subshell. The third quantum number M sub L اللي هو الرقم الكمي المغناطيسي. القيم اللي بياخذها اللي هي from minus L including 0 to plus L. يعني إذا كان عندك L equal 1 على سبيل المثال 1 معناته M sub L from minus 1 to plus 1 including 0. We have three values, minus 1, 0, and plus 1, and so on. M sub L is related to the orientation of the orbital in space, يعني اتجاه الفلك في الفراغ, relative to other orbitals in the atoms. This table gives you an idea about the value of L and what letter we used. When L is equal to 0, we have S orbital or S subshell. When L is equal to 1, we have P subshell. When L is equal to 2, we have D subshell. When L is equal to 3, we have F subshell. When L is equal to 4, we have G, and then after that, here the letters are alphabetics. This table here summarizes the quantum numbers for the first 4 levels of orbitals in the hydrogen atom. The first column, which is the principal quantum number N. The second column, the angular momentum quantum number L. The third column, the sub-level designation. The fourth column, the magnetic momentum quantum number M sub L. And the last column here we have the number of orbitals. When N is equal to 1, the L value will be 0. Only one value, because L takes from 0 to n minus 1, only one value. then the sublevel designation will be 1s, because L0 we have s orbital, and 1 because the n principal quantum number here is 1, so we write the sublevel as 1s. M sub L value from minus L to plus L including 0, only one value. So number of orbital will be 1. Each orbital can accommodate 2 electrons, so s orbital accommodate 2 electrons. When n is equal to 2, L value will be either 0 or 1. For 0, we have 2s. For L equal 1, we have 2p. Because L1, we have p sublevel. And 2p, because we have principal quantum number here is 2, then we write 2p. M sub L for L equal 1 from minus 1 to plus 1 including 0. So we have 3 values, which means we have 3 orbitals. 3 times 2, 6 electron for p orbital can accommodate it. When n is equal to 3, L value either 0, 1 or 2. For L equal 0, we have 3s. For L equal 1, we have 3p. For L equal 2, we have d orbital and designated as 3d, because principal quantum number here is 3, then we have 3d. For M sub L value, it takes from minus 2 to plus 2 including 0. We have here minus 2, minus 1, 0, plus 1, plus 2, 5 values, which means that we have 5 orbitals for d orbitals. 5 times 2, 10 electrons for d orbitals. Last thing here, when n is equal to 4, L value will be 0, will be 1, 2, or 3. For L equal 0, we have 4s. L equal 1, 4p. L equal 2, 4d. L equal 3, we have 4f. Because n equal 4, then designated as 4f. M sub L value from minus 3 to plus 3 including 0. Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So we have 7 values. We have 7 orbitals for F. Each orbital can accommodate 2. 7 multiplied by 2, 14 electrons for F orbitals. Here we have an exercise for a principal quantum number n equal 3. Determine the number of allowed subshell different values of L and give the designation of each. N equal 3. L value takes from 0 up to n minus 1. So 0 up 3 minus 1, 2. 1, 2. So we have here L value 0, we have 1, we have 2. Subshell designation. When L equals 0, we have s orbital, then we have 3s. When L equal 1, we have p orbital, and this will be 3p. When L equal 2 orbital, and this will be 3d. Here also another exercise, but it's solved. For n equal 5, we have to determine the number of allowed subshell different L values. Same thing, n here equal 5, then L value from 0 up to 4, because 5 minus 1 will be 4. So L value 0, 1, 2, 3, 4. When L 0, we have 5s. When L is equal to 1, we have 5p. When L equal 2, we have 5d. When L equal 3, we have 5f. When L equal 4, we have 5g. This slide shows the orbital shapes and energies. Let's start first with the s orbital. S orbital has a spherical shape, شكل كروي. Figure 713 here, we have two representations of the hydrogen, one s, 2s, and 3s orbital. A of this figure shows the electron probability distribution. You see here, finding electron in the 1s, here we have a dark area in this area. In 2s, we have a dark and we have white area. This called a node, يعني عقدة باللغة العربية. Finding electron at node area is equal to 0. The 3s orbital, we have two white areas, two nodes mean. Finding electron at these areas is equal to 0. As n increase, the size increase of A. Part B of this figure, we have the surface that contains 90% of the total electron probability. As n increase, size increase and the energy increase. Second, we have in figure 714 a p orbital. As we know, p orbital, they are 3 orbital. The shape of p orbital like a loop or infinity. In the Cartesian coordinate, we have 3 coordinates, x, y, and z. If the loop along x, we call it px, as shown here in the figure. If it's along y, we call it py. If it's along z, we call it pz. And the node here in this area. So finding electron at this point is equal to 0. Third, here the shape of d orbital. Figure 716 here, representation of the 3d orbitals. As we know, d orbital has 5 orbitals. These are dxc, dyz, dxy, dx square minus y square, and dz square. The shape of d orbitals in general, two loops together, here a positive, here a negative. dxz means in the xz plane, yz in the yz plane, and so on. dz square along z, you see here the positive, and this loop is a negative. So we have more complicated shapes than S and P, even though for F orbitals also the shape becomes more complicated. This area or this point is called node, and finding electron at this point is equal to 0. Now section 7.8 electron spin and the Pauli principle. اللي هي الحركة المغزلية للإلكترون ومبدأ باولي للاستبعاد. نتيجة للحركة المغزلية للإلكترون راح يتولد مجال مغناطيسي. If the movement of electron clockwise مع عقارب الساعة، مجال مغناطيسي بيكون اتجاهه للنورث وبيكون M sub S للإلكترون equal positive half. If the movement of electron counterclockwise عكس عقارب الساعة بيكون اتجاه المجال المغناطيسي للجنوب وبكون عندي m sub s is equal to -half. هذا اللي هو الرقم الكمي الرابع، وهذا طبعا experimental يوجد طبيعي. كمان مرة بذكر اللي هم ال N وال L و M sub L هذول theoretical calculation اجوا من حل معادلة شرودنجر، والرقم الكمي الرابع هذا experimentally. So the Pauli exclusion principle, in a given atom no two electrons can have the same set of 4 quantum numbers. يعني ما في أي توزيع إلكتروني لأي ذرة إنه يكون عندي إلكترونين لهم نفس المجموعة الأربعة من الأرقام الكمية الأربعة متساوي، لازم يختلفوا على الأقل في واحد. An orbital can hold only 2 electrons and they must have opposite spin. In this slide, just to remind you, an orbital can hold only 2 electrons and they must be opposite spin if they are in the same orbital. S orbital 2 electrons, P orbital maximum 6 electrons, D orbital 10 electrons, F orbitals 14 electrons. Example here, which of the following sets of quantum numbers are not allowed? The first set here, n equal 2, l equal 1, m sub l minus 1. This can be, but here ms is 1. This is not allowed, غير مسموح. B set, n equal 3, okay, l equal 1 can be. In L equal 1, then M sub L could not be 2. This is not allowed. Should be 1 or 0 or minus 1. C. N equal 5, L minus 4. This is wrong. Cannot be L here because L from 0 to N minus 1. This is not allowed. D. N equal 2, L equal 2. Same, L2 here incorrect. And E, N equal 3, L equal 1, M sub L -1, M sub S -half. This is allowed, correct. The last slide here we have some questions to answer. Number 1, in an atom, how many electrons can have the quantum number designation? N equal 4, M sub L minus 1, M sub S minus half. N equal 4 means L equal 0, 1, 2, and 3. For L0 we have S orbital. L1 we have P orbital. L2 we have D orbital. L3 we have F orbital. So we have the second requirement here, M sub L is -1. So for L equal 0 there is no M sub L -1. Here we have 1 orbital, we have 1 orbital, we have 1 orbital. So we have a total 3 orbitals with M sub L -1. And M sub S is -half, so we have here 1 electron and 1 electron, 1 electron. So the total number of electrons will be 3 electrons. Question 2, here fill in the blanks. You have to memorize this statement. No two electrons in the same atom can have the same set of 4 quantum numbers. Is a statement of the answer is Pauli exclusion principle. مبدأ استبعاد Pauli. Number 3, calculate the wavelength in nanometer of the radiation that has energy 3.60 10 to minus 19. You have the formula. Lambda is equal hc over delta E, where h is Planck's constant, c is speed of light, delta E, which is the energy, is given in the question. Here, 6.626 times 10 to minus 34 joule second multiplied by speed of light 3.0 10 to 8 meter per second divided by delta E 3.60 10 to minus 19 joule. The net result from calculator will give you 5.52 times 10 to minus 7 meter. We need it in nanometer, so multiply this number by 10 to 9. This will give you 552 nanometer. Thank you. Bye.